So hi, yeah, today I'm going to talk to you about a project of mine which is called Drand. Basically, this is a distributed bias-resistant, unpredictable, and publicly verifiable randomness network, which is a long, very long title, but we're going to go in details to see what does it mean. So I want to talk about randomness in general first. So why do we need randomness in the first place? So either in the, let's say, the real life or in our digitalized world, we need it. So for lotteries, for jury selection, for election event audits, for example, I don't know if you recall, there was some buzz around when Trump was elected about which counties we did verify and not, these kind of things. Randomness was not unbiasable at all here. For protocols and cryptography, this is one of the main application of good randomness. For example, parameters, cryptographic parameters when we want nonces, when we want for symmetric encryption, or derived parameters for based one on elliptic curves, for schemes, for signature schemes, for defilement schemes, and so on. Zero knowledge proof, we often need randomness. For more, let's say, developed protocols like consensus algorithm, for example, leader election, proof of stake, we need publicly verifiable randomness. In Tor, to choose which we need randomness there as well. For sharding blockchains as well, there are some protocols that use publicly verifiable randomness in this way. For statistic as well, for everything that is sampling, reducing bias, even for clearancy and divination. So just the point here is that randomness is an important part of a lot of protocol, either in real life or in the digital or in the internet. Now, why do we need good randomness? Because there's been a lot of stories with bad randomness. That's the main point. One of the biggest fraud, I think, that brought one of the most one of the most expensive attacks was like on the Lotto of the US Hot Lotto fraud scandal. That one guy that was an insider has been able to steal $14.3 million. All of that because it was a rigged pseudo number generators. There's also, like, for example, another let's say story about suspicion about the NSA that has been that has selected some parameters in such a way that it may lead to some vulnerability in the cryptographic scheme, and there is no way to verify that. Even from the side of the attacker, like, for example, ransomware needs some randomness to encrypt the hard drive. And where do they take it usually? Well, most of the time, let's say the bad ransomware take it from the timestamp, and this is very easy to try and brute force and try to decrypt afterwards. So even from like I say, the other point of view, even attackers need good randomness for attacking. So what do we have now? What exists now to create good randomness? So usually we have what we call a CRSP-RNG, a cryptographically secure pseudo-random number generators, and there's some cryptographic definitions that says that defines how unpredictable it is or random it is, let's say, and usually the way it works, for example, on your every high-end computers, usually you inject external randomness into the systems, and then so the entropy is resourced, let's say, the entropy resource is reseeded, and you generate new kind of entropy. For example, it could be the what you type on your keyboard, it could be the network events, and so on. The Linux kernel has plenty of different sources. But even then, there are still some potentially catastrophic behavior. Like, for example, recently, I mean, I think it was 2 years ago now, there was this attack which is called GUG, which which attacked Juniper VPN services. And so VPN is used in a lot of places, and they used the fixed hard-coded seed key for that, and there was no mechanism no mechanism implemented to inject new entropy into the system. So they were able to decode traffic. So now there's like different kind of randomness, and now in this talk I'm gonna talk mainly about one kind, which is what I call publicly verifiable. So that means anybody can verify it's a legit random number. Okay, you get the random number. I can verify it's been generated accordingly to the protocol I'm going to describe later on. Good randomness should be unpredictable. That means the same cryptographic assumption than the CSP energy, for example. You should not be able to predict what the next output will be. It could be bias resistant. That means even if I'm an attacker, even if I'm a powerful attacker, I will not be able to choose one value over the other. If I only have two values to choose from, I shouldn't be able to choose between the two or even more. This randomness. We want a set of independent and diverse parties across the web to generate this randomness. And of course, it should be available. I mean, if I can't reach the system to get my randomness, it's useless to have it. So available is also one property we want there. So what's out there right now in terms of randomness, that is of external services that produce randomness? Let's say some example I listed here is like there's a NIST randomness beacon, for example. So it is a governmental entity of the US government, and they have this kind of a quantum-based random beacon where the entanglement is used to derive random numbers. So there's definitely it's definitely unpredictable thanks to the quantum laws. Unfortunately, we still need to trust NIST. There's no publicly verifiable. The property of publicly verifiable is not enforced. If I contact NIST servers, they can give me any random number they want. I will not be able to verify it really comes from their quantum systems. So another source of randomness that has been trying to be used recently is more on the blockchain wars, like using Bitcoin. You derive randomness through all the blocks in the Bitcoin blockchain. It looks promising. There was at the time, I think now it changed a little bit. At the time, there was not formal proof of security, and I think it showed. There was also another paper that showed that randomness was not good enough to be called unbiasable, to have this property that I showed you before. There was also there was a protocol which is called Drand, which claims to be a scalable, bias-resistant, unpredictable, and publicly verifiable decentralized protocol. So it looks like there is a jackpot. Unfortunately, let's say it relies on solid. It offers probabilistic guarantees, and it has a very complex setup. It has very large transcript to verify. I mean, as a client, to use the service, I need to verify a very large transcript of multiple exponentiation and so on that take time to verify. It takes multiple round trip between the participants. There's different phase of the protocol which can lead to various bugs, and it's kind of slow in the sense that it leads to at least, and the paper shows a 6-second generation. So this question I'm gonna try to answer here is like, can we do a simpler and faster protocol that have the same guarantees here? So here I'm introducing Drand. So what is Drand? Drand is a software that is run by independent nodes that collectively form a randomness as a service network. So that means they periodically produce randomness, which is publicly verifiable and all the other properties mentioned before. So the goal of Drand is it's a software. So and the goal of Drand is to be randomness as a service as simple as what NTP servers are now for today. So NTP servers, for those who don't know, is like just servers around the globe that provide the time services. So when I connect on the internet, my computer can fetch the time from one of these services and set the time accordingly. And the goal is to be able to have the same kind of services for randomness. Now, Drand have both kind of randomness. Let's say what I call private randomness, so randomness which is not publicly verifiable. For example, this can be used in it can be useful for embedded devices. which have a very low entropy sources at the beginning when they boot up, let's say, and they need to gather some external entropy to the system. It's very difficult in some scenarios for embedded devices, and it also the main point of this talk is also delivers public randomness, so which is unpredictable, bias resistant, and publicly verifiable. So in short, this Drand is uses a threshold cryptography. We're going to go a little bit into the detail right after, and to ensure this above properties. Another key point of Drand is that it can act as a glue between different entropy sources. So let's say you have the NIST entropy sources, you could have the Bitcoin entropy sources, you could have any other entropy sources that you could use as a seed to run a Drand network, and the Drand network will output still a publicly verifiable randomness. So it still incentivizes the development of any other entropy sources techniques. For example, post-quantum techniques. There's a lot of companies that are developing post-quantum techniques now for generating randomness. So, oops, do you see the screen? Looks black to me.
It's all black. Yes.
Yeah.
Yeah.
Black. Oh.
Okay. Yeah. Okay. Let's do this. I don't know why it's black.
Okay. Now.
Okay. So let's go a little bit into how does it work. It's not going to be hard math. It's quite simple to understand. So I'm going to go over it slowly. So at the basis of this of Drand, there's what we call Shamir secret sharing. So the goal is I have a value that I want to split into some shares, such that in order to reconstruct this value later on, I need at least T out of n shares. If I create n shares, at least that needs T. So let's say I create 10 shares, I will say that I need at least 7 out of 10 shares, any of these 10 shares, to reconstruct the initial value. So how does it work is that you create a polynomial of degree 6. Let's say let's stick to the example of I need set shares out of 7, and you create a polynomial of degree 6. You put the first coefficient, so S, as you can see here, will be my secret value. And then you just evaluate 10 shares. So f of 1 will be the first share, f of 2 will be the second share, and so on and so on. So afterwards, if I want to recreate the first my secret S, I just need to interpolate the share. So I take any subset of 7 shares, and I will run them through what we call Lagrange interpolation to recreate the original value S. Actually, you can recreate the whole polynomial f of x here. That's the basic of Shamir secret sharing, because the underlying theory is that if you have k points, you can reconstruct uniquely a polynomial of degree k minus 1. So this is why you can use any subset of 7 out of 10 here shares. So now we go a little bit deeper into this scheme, and we generalize this scheme. So instead of having one secret that I share, I will have n secrets that I share in parallel. Okay, so there will be not one participant that creates a secret here. There will be n participants, but each of them will create a polynomial here. Okay, a different polynomial. Okay, but they all will choose a secret here. The first participant will choose S1, the second participant will choose S2, and so on and so on. And at the end of, so there's a protocol when you distribute the shares to everybody. And so I will not go into too much detail here, but basically you, as the first participant will create the shares with this polynomial for S11, S12, S1n. So S12 is the share destined to, is a share for the second participant created by the first participant. And so each participant will broadcast in an encrypted form their shares. They'll broadcast other things as well, but I don't want to go into much detail. And at the end of this protocol, you will add all these shares received. So as a first participant, I will add all the shares received for me. If you see S1 is the shares of S11, S21, SN1, okay? And in the end, at the end of the day, what you get out of this this protocol is you get a share that if you aggregate a threshold of these shares together, it will reconstruct a secret that nobody knows. So this it's basically the secret is the addition of S1, S2, Sn, and so on, the things that you see at the left. This is the final secret, but nobody computed the secret in any places. But the key point in this distributed key generation is that you have some kind of a private key which is shared, and nobody knows what this private key is, but you still have a public key. And what the nice thing is that this public key is just the evaluation of the public polynomials here. So basically, you commit to each party commit to the polynomial. So as F1 will be committed by multiplying by using a polynomial commitment scheme, and this public polynomial will be one part of the public key, and then anybody can know the public key. It can be computed by anybody. So the two main key points is that there is a private key that nobody knows. Everybody has a share of it, but everybody knows the public key. And that allows you to do many fun things and to decentralize many protocols. This is a key point of Drand. So this is exactly, Drand works in two phases, let's say. There's like this setup phase, which runs this distributed key generation protocol. And right now, Drand use the first Peterson DKG protocol. It originates from the Dedis cable library, where I was a research engineer 2 years ago. So how does it work is that you have a bunch of nodes. I want to create this network, then we'll run this setup phase. It's the most expensive setup phase. It's O(n)². It's basically an MPC, and this MPC complexity is O(n)². You set the threshold as much as you want. Actually, you set actually the threshold is superior to n over half. Here, there's a mistake. So you set the threshold as much as high as you want. It must be more than 50%. So if, for example, to take our example before with 10 nodes, you can't set the threshold to 4. That's too low. The cryptography is not meant to be secure in this case. So the threshold is at least 50%. Right now, Drand implement this setup phase using BLS 12381. It used to be BN256, but I changed it recently because there was some concern about the security of BN256. And as I said before, at the end of this setup phase, everybody has a share of the distributed secrets, and everybody has the associated public key. So let's see now what happens in the second phase, in the randomness generation phase of Drand. So I will introduce now what another notion in cryptography, very high level, but I think it's quite simple enough to understand here. It's like what is called pairing-based cryptography. So in pairing-based cryptography, usually you have 3 groups, G1, G2, and what we call GT, such that there's a mapping between G1 and G2. You can take a tuple from 1 point in G1, 1 point in G2, and it maps you to 1 point in GT. Okay, and this mapping, which is called the pairing operation, and simply with this mapping, with this special construction of 3 groups and this bilinear mapping, then we can construct a very efficient signature scheme. The most well-known one is BLS signatures, which has a lot of interesting properties. I will not go over all of them, but right now, what is interesting is that the signature is only one single element. So the signatures is just 1 point in G1 or in G2, actually. You can switch over the two. So when I sign a message, I just hash the message with using a hash function, so SHA-256 or whatever hash function you want to use. And then I just multiply it, or here it's exponential form, but just multiply it by my private key. Okay, and that gives me the signatures. That's it. Now the verification, I need the public key, I need the message, and I need the signatures, and I will just use this mapping, this bilinear mapping that I introduced before. Okay. And if you add down the details of this equation with a pairing equation, you see that that both sides are equal when the signature is correctly computed. So what is interesting for BLS signatures is it can be adapted into the threshold setting. So instead of having one private key, each party could have a share and still do a BLS signatures with each share. Okay, so it will result in having in each party create a partial signature, what I call a partial signatures, because it's not a complete BLS signature, it's a partial signatures. And then when you collect T out of these partial signatures, you can aggregate them the same way as I explained in Shamia Secret 7. You can aggregate them into one final complete BLS signatures. And this BLS signatures is the same as a normal BLS signature scheme. Like it would be the same as if you really had the distributed private key in hand, but nobody has it. So so to enforce. So now this construction has a very interesting property is that to be able to sign something after you created this distributed key thanks to the protocol I showed before, you need it enforces that you need T out of N to create the signatures. So you cannot do anything if you don't have T nodes that output a partial signatures over a message. You cannot create the signatures. Okay, this is like the main key point of this threshold BLS signatures. And this threshold BLS signatures is exactly what we use for randomness in Drand. So the hash of this BLS signatures, this threshold BLS signatures, will be the randomness. You just hash as the signatures. And thanks to the property of BLS, since it's unique, you can prove that it gives a non-predictable and unbiasable randomness. So now you get the whole stack of it, and this is like just this slide is just to explain how basically does it work in the protocol works in Drand. So it's very simple protocol. Like as a node, I will contact at least T out of the rest of the nodes in the network. Partial signatures, I reconstruct them locally, and I store the randomness, and that's it. So it's a simple fetching protocol. Very like it works with HTTP requests. I just contact T nodes at least. As long as I have T partial signatures, I can reconstruct the final. Publicly verifiable. So if I have the public key, the distributed public key as shown before, I can verify the BLS signatures. It's decentralized because you have to enforce it, but it's a different set of nodes. At least T out of N needs to participate into this protocol to generate the signatures. It's available under the threat model. So if you assume that you have at least 50% of nodes that are honest, then this honest node will always be able to generate these signatures, and the signature will always be still unpredictable and unbiasable. And it's quite fast. I mean, the time to it's only one RTT that you can do in parallel to T out N nodes. And you have to do one language interpolation. So the language interpolation will be the main bottleneck factor here, depending on the size of the network. Depending on the threshold actually, because the language interpolation will the complexity of the language interpolation depends on the threshold of the polynomial. So as Drand, Drand is a software written in Go. We'll talk more about practical issues now. We leave a bit the cryptographic side, and we talk about the practical things of Drand. So Drand is an open source software written in Go. It's hosted on GitHub. It originally comes from Dedis. So when I was working as a research engineer, I started Drand there. Now it moved to independent organization on GitHub. Is meant to be really simple to use, both from the operator's point of view and the client's point of view. Right now, it's focused a lot on the client's point of view. So basically, just you have it uses gRPC, but you have a JSON API. So just you do a curl. Basically, it's a HTTP request / you take the node address of the node is /API/public, and you get the public randomness. That's all you need. So you can use it in JavaScript application as well, for example. And there's one command for doing the setup between the node, and there's one command for doing running the run generation. Actually, now there's only one command for everything. Of course, there's tons of subcommands for sub cases where we want to go there, but I will not go into details here. So as I said, it uses gRPC with protobuf or a TLS connection right now. The software is meant to evolve, so there's also some discussion potentially to use libp2p, since now I'm working as well more closely with libp2p teams. It could be interesting to see how that evolves. There's Dockers as well that you can use for running Drand. It has the, as I said before, it has the ability to inject external entropy into the system. So I will go a little bit more in detail into this one. So you will, right now, Drand allows to inject external entropy during the setup phase. So when you create these polynomials that I showed before, this F1, F2, Fn, this S1, S2, Sn can come from any sources at all. So for example, I could have a quantum number generators that create this S1 for me, okay? And I could input them. Nobody knows that, but me will know it if I own the quantum number generator. But it means I can bind different entropy sources into this distributed key generation protocol. And right now Drand allows to do that via a simple command line argument. So as long as you have a script that can fetch this randomness, it can put you inside it can make sure that the setup phase will use this randomness. As well, it's still work in progress. It's a living software, so if you are interested to contribute, there's plenty of issues to fill in, and happy to talk about it more afterwards. About the running network. So there's currently a running network of Drand instances. It went live last June in 2019 under the name League of Entropy. So it was kind of a, we contacted Cloudflare, they were really interested, and we kind of divide the superhero names for this network live. You can go to leagueofentropy.com and you get all plenty of information on this. Protocol Lab is participating, Cloudflare, EPFL, QSKey Security, as well. No, it's a non-exhaustive list. I think we are 8-9 members now. It's still relatively small. The future is to expand more and more. I will go in a little bit into details after that. Right now, Cloudflare participated into the setup phase using its lava lamp wall. I don't know if you ever saw this or if you heard of it, but basically there's a camera that scans all the lava lamp movement, and lava lamp movement is very hard to predict. So it's kind of seem to be as an unpredictable source of randomness, and they inputted that randomness into during the setup phase for the last setup. So that's the current network that you can play with. Actually, I wanted to show you. I will share just one thing here. Let's hope it works. If I do a demo today, it will be very small, but you should see my command line here. And if I contact protocol AI, so protocols labs instances, it should output this JSON file. So you see we are at around 361,351, and this was a previous randomness, and this is a new point on the curve. So basically, the API will change a little bit. Now it will be much simpler in the next version, but this is the final BLS signatures that you need to hash to get the randomness. This point is one. And this is actually, I realized one point I didn't mention here is the way the randomness is chained. Let me go back to the presentation. So the generation. So as soon when I want to, the randomness generation works by round. So there is like round 1, round 2, round 3, and at each round I will take the previous randomness generated. I concatenate it with the round number, and this is the message I will sign. This is the message I will create a partial signature for. This is the message I will ask for my other peers, and then I will get this partial signature. So we have a chain of randomness basically, and this whole chain is unbiasable because of the properties of BLS signatures. So where was I? During the network, yes. So during the future, let's say what I try to push for these networks is that in terms of the network, I'm trying to bring as much as possible diverse and independent organization to the network. We have some interest from NIST, from some blockchain companies, as well from some post-quantum security companies, namely some that generate post-quantum that has post-quantum randomness generation that want to contribute to the network. We are trying to plan a next release of the network soon, but we want to bring as much as possible interesting parties to the network, because it's kind of a semi-permission network, because you have to know the public keys of everybody to run this setup phase. And in terms of on the service, we want to binds multiple entropy sources. So for example, I'm trying to talk with NIST or other companies to see if they can actually input their entropy around their source of entropy into the setup phase, so that Drand can really act as a glue between all these different randomness entropy, because there are quite a while actually online, if you search a little bit, that propose randomness services. There's even like a poker company that scratch message on forums and on social media to generate randomness for their poker online services. So there's like many things to be improved, and I think we could there's like a lot of also ways to go there. And I think that's it for me. We'll keep it short, and if you are interested into participating, or I'm happy to chat with you later on. Thank you.
So let's go ahead and if you have any questions, you can chime in, would be the best thing. If you're feeling a little shy about speaking on the recording, just type your question into the chat. And then Nicolas, if you answer any questions in the chat, just go ahead and read the question out loud first for those watching in the recording.
Sounds good. If I don't see them, point me to it.
Sure.
I had a question. Also, hello, Nicolas. It's lovely to see you again.
Hi. Yeah, nice to see you, Michael.
I was wondering, you'd mentioned sort of like injecting entropy, and I think my question was if the injecting entropy sort of presented an attack vector, but then it sounded like the only time you would get to do that is during the actual setup of things, in which case, like, you can assure that you have enough control over the network that that doesn't actually present a problem. Is my understanding correct?
Generation.
Sorry, say again.
Yeah, I think my connection got a little bit. So this distributed key generation is, given the threat model and the network assumption, is secure as long as you have more than 50% of honest participants. So if you are a malicious person, even if you put 0 as your secret, it will not impact the distributed key generation. There are some results that shows that this specific type of distributed key generation, like the one that I mentioned, Peterson one, can be biasable into some extent, but it doesn't impact the distributed when you use it in the context of threshold signatures. There's like a proven result that say even for this particular DKG can be biasable to some extent, and there are better, like let's say, not better, but stronger DKGs that, but more complex in terms of protocol as well, that try to remove this bias. There's another paper that says even for this bias is there, it doesn't impact the biasability of the signatures. So the signatures, the randomness basically will still remain unbiasable.
Cool.
If I may ask one question. Cool. So thank you so much for this presentation. I'm still I'm still grabbing the pieces of my brain because it exploded through it. Really, really cool and really advanced stuff. I'm thinking like from the perspective of a user. So you mentioned like this is like a very good tool for gossiping, right? Because you can pick any random node, and therefore like you can prevent attacks from other nodes that are trying to eclipse some part of the network, some path of the network, etc. But like from the perspective of the user, I'm curious to understand where, let's say I have a gossip network, and like each of my nodes is picking one random number from like this league of randomness, league of entropy, sorry, and now I do have a number, and so now I can pick some node randomly. But like when I pick that node, what exactly do I like tell the rest of the network so that they can prove that I actually fetched this right like random number from this service? Like, how does this verification happen from the use case standpoint?
So first of all, like I said before, I think there's two kind of there's two kind of randomness. Let's say what I call private and public randomness. Like there's some use case where you don't need for the randomness to be public, and you want it to be private and only known to you. And in this case, you just take the view random. You just take your quantum sources or whatever. Okay.
Yeah.
That's the only thing you can do because you want it to be private. So you contact a large number of Drand instances, and then you aggregate them all this randomness together. Because if you contact as more than T nodes, then you can be sure that there's at least one honest. So the output will be random. There's actually a Python library that tries to do that and inject the randomness into the Linux kernel. One guy that called it this. So that's one thing. So not all use cases will use a publicly verifiable randomness. First, that's one point. If you do want to use a publicly verifiable randomness, then indeed you need to have a, so it's an interesting use case here. You need to show how did you use a randomness. So like everybody will know the randomness, so you don't even need to send it to them, or you just say the round number and they can then fetch it from Drand itself themselves. So you say, if you tell it, I use a randomness at round 10, then I will fetch it and verify that the randomness is correct. And then I need to know how did you use it. That depends on the use cases. I cannot answer I don't have a generic answer for this. It completely depends on the use cases. So as a gossiping application, since you will use a network, I agree it's maybe a little bit tricky to prove that you did the correct shuffling. I think like the private randomness fits more in this type of use cases here.
Okay.
But maybe with some timing assumption, like let's say if you have very large time, like say I pick one node, I send it for the first 2 seconds, another node in the first 4 seconds, and so on. Maybe you could do some trick here, but it's like not sure it fit exactly the public randomness case. In my mind, yeah.
Okay, gotcha. Thank you for the answer.
I actually have another question. That's all right. So in the mode in which you mentioned that you can bind together several non-publicly verifiable entropy into this sort of a public verifiable randomness. So you mentioned several non-public sources of randomness. So I wonder what does these several mean and what are the assumptions there? Can it be only one? Does the security increase as the amount of sources increase as well?
So let's say in terms of security, of guaranteeing these properties won't change regardless if I use dev urandom or my own local generator or from my own computer, or regardless if I use a quantum number generator. So let's try to go into a bit more details here. So let's say if nobody uses quantum number generators, if now let's say in the other way, if everybody uses quantum number generators, it doesn't mean that, for example, that Drand is quantum resistant, because Drand cryptography is not quantum resistant at the moment. It's one of the key points that we have to research on how to evolve Drand's techniques into being quantum resistant. If some of them use the quantum number generators, that means these seeds here, S1, S2, Sn, will be of view. It's to quantum rather than using my own local generator. So it means that as a result, my private key will have I don't know exactly how to say it here. My private key will contain more entropy than
Nicolas,
if I didn't use.
I think you've glitched for everyone for like 20 seconds, so you might have to repeat your answer.
Yeah, so I was saying that if some nodes create this polynomial using the secret that is taken from let's say from a quantum number generator, that means the resulting distributed private key, so that nobody knows, will have much more entropy than if everybody use our own local random generators. So in this sense, the whole random chain will have more entropy. It doesn't mean that if you don't only use dev-random, it's insecure, because we believe using dev-random with sufficient entropy is secure anyway, because we have proven cryptographic CS per NG that have these properties, the next speed step properties, and so on. So it doesn't mean it's insecure, but it means we are much more higher entropy into the service if you use quantum generators. Nevertheless, even if you don't do it, it will still be unpredictable and bias resistant on the protocol level. So it's like it's a subtle distinction here, let's say.
Cool, thank you.
I have one more. So you mentioned that the League of Entropy started with like 5 or 6 partners, but now there are many more. How does that transition happen? Like, is there a way to increase the number?
Yeah, so it's
yeah,
that's a good question. It's something that is missing from this presentation, I see. It's actually so there is like this setup phase. Actually, this distributed key generation can be slightly adapted. It's the same protocol, but some slight difference to actually reshare a share that I already have. So you do a new setup phase from one group to the other, and the two groups can be completely disjoint, can have a completely different numbers of nodes. Actually, it must be, there's some not completely, it must grow, and if you shrink down the group, you must still sure that you still keep the right amount of nodes regarding to the threshold that you had before. There's some subtleties here, but basically these two groups can be completely disjoint. You can pass from 10 groups of nodes to another completely disjoint 10 over group of nodes, and that's the same setup phase actually. I don't call it setup phase. In Drand, if you go into the GitHub README, you will see it as a resharing phase. So you the old group, you give a new account, and we launch this command, everybody raise, and then the new group is active. And the nice property that the public key, the distributed public key, the science perspective, nothing's changed. I can still use the same public key. I use the same, I use the same public key. Namely, only the endpoints might change, because obviously there's some nodes that are done and some nodes that are new. But there's no change in the code required, let's say, or to change the public key from a client's perspective. Like generally, when you update keys, you need to change the keys. Like, I don't know if you ever updated your GPG keys and stuff like that. It's a nightmare, and then you see it with your package manager. On this case, you don't have to. It will be the same public key, but you still updated the group.
I'm not sure if I completely understood. Well, first, because like you cut it a little bit, but also I'm not sure if I have the right model in my head. So you've mentioned that you have the first group, and at a later stage, a new group joins, and they might not even talk with each other, but they use the same setup phase. So the second group is going to copy the results of the.
Sorry. I need. Okay, let me go over. I will do a bit more detail. So they will run this, both groups will run the same distributed key generation protocol, a slightly variation of it, okay? They will run the same, so they will communicate with each other. Basically, what it means is that instead of having a new S1, S2, Sn here, instead of having a complete fresh random secret, they will put their shares, the whole group will put their shares here. And instead of distributing the shares F1 here, F12, F1n, etc., instead of distributing to the same group, they will distribute it to the other group. So the other group, we are the shares of the first group. Okay, basically that's what I mean in a larger sense. So it's a slight variation of the DKG protocol. It's a paper written about it. So in effect, at the end of the day, you still get the same public key, but the both group will have, after the both group will have run this setup phase, the new group will have the new shares, and we will still get the same distributed public key. The old shares will not be, let me pause 1 moment. The old shares will not be, I mean, assuming still the threat model is respected, so there's more than 50% honesty, but will either go into the new group or either drop out. Mm-hmm. The old nodes will not be able to use the old shares anymore. Only the new shares will be able to be used.
Gotcha. I had previously understood that like each of these, well, does that mean like in order for the group to grow, it needs to like grow by a factor of 2? So like given that the old nodes need to kind of like do the ritual of passage, or for lack of a better term, to the new group, does there needs to be like a one-to-one mapping between like the number of shares that existed before to now the shares that need to be created for the new group?
No, not really.
Okay. Okay.
It's like in the usual distributed key generation, everybody has the same role. In this variation, holders, and the dealers are the nodes from the old group, and the shareholders are the nodes from the new group. And they can be, the numbers doesn't matter. I mean, there's some minimum threshold to attend on both, but it can be completely different set of nodes. And the dealers will create these polymers and create the shares and will give them to the shareholders, basically. So it's like this transition of shares. The shares are created in a slightly different way here. Basically, as I said before, the S1 will not be a completely new random element. It will be the share I have. As if I am the first node on the old group, I will put my current share here and I will share my share, basically. So it's a slightly different variation, but it gives the same, it's using the same protocol in essence.
Interesting. So that means like that the new parties that join the League of Entropy are actually not creating interesting random generators, right? Like they don't have to create the lava lamp random generators anymore.
Not at all. I mean, you can use whatever you want. I have my server running. It used its own local Linux kernel generator. I mean, it's fine. I mean, it's just that it can be. I'm putting this as a properties of the network because I think it's very interesting to be able to still promote different sources of entropy, because there's a lot of companies and universities that are promoting their own sources and at the same time glue them together into some kind of unified network. And yeah.
Do a last call for questions here. You got about 5 or 10 seconds if you have more to ask.
Well, in any case, I'm always happy to talk about Drand. So you can find the info. And yeah, please contact me if you have any question. I'm happy to answer.
Nicola, I think this one might have just been me and not everybody, but since I'm recording it, you can find the info and then froze. And
sorry,
then
you can get the info at github/Drand, the URL shown here.
Oh yeah, right on the slide. I was watching.
Yeah, sorry
your face.
for the internet. It's weird.
No problem. Great. Well, thank you so much. This was fantastic and really appreciate it, and great turnout. Thanks everyone who joined us. I'm going to just cut out the recording here.